So in the last class we have already discussed about the Bernoulli's principle, and we will discuss one of the some applications of the Bernoulli's principle. One or two applications that is very important. One such is, suppose I have a large tank filled with water. It is filled with water up to a certain height. There is a large tank which is filled with water up to a certain height. Let us consider this height is from this bottom level, this height is h1. Consider this height from the bottom level is h1. The area of cross section of this portion is considered as A1. Then we consider if a hole is prepared at the bottom of the tank, then water will come out from this portion. Now, then water will come in this way, like this. We consider that this hole is of area of cross section A2 and its midpoint is considered to be at a height very small, that is considered as h2. This height is considered as h2. The center of the hole from the bottom of the tank is at a height h2. This one is at a height h1. This area is A1. This smaller hole area is A2. Now we consider that through this point water will come out with a velocity v2. Water will come out with a velocity v2. Then from this portion water will come down with a velocity say v1, because as water is coming out of this hole, this height of the water in the cylindrical tank will decrease. So this top surface will come down with a velocity say v1. Now in this case, if we apply Bernoulli's theorem, then we can find this velocity. Once this velocity and height, all these things are known to us. And remember, this V2 will be a very surprise. The result of V2 is a very surprising result. Check. I consider now Bernoulli's theorem. Bernoulli's theorem says that total energy density at any point will remain constant. Now in this particular case we consider the streamline motion and it is a Newtonian fluid, so we apply Bernoulli's theorem. So at this point if we apply Bernoulli's theorem, we can write P1 plus half rho V1 square plus rho G H1, that is equal to P2 plus half rho V2 square plus rho G H2. Okay, rho G H2. Then we can consider that P1 and P2 for this tank are equal, because it is a tank filled with water. So at this point and at this point the pressure is the atmospheric pressure. Just at this point the pressure, and at this point pressure is just the atmospheric pressure. So tank is that not much height. height of the tank is not so great, we can consider that pressure here and pressure here will change. So atmospheric pressure with high gain with decrease with altitude, but a water tank, how much its altitude can be? It is very small at top and bottom. So that's why we can consider both have almost atmospheric pressure, and as a result this P1 and P2 both can be written as P atmosphere, and as a result we can cancel this. Okay, now we want to write here that rho G H1 minus H2, that is equal to half rho V2 square minus V1 square. Okay, rho G H1 minus H2 equal to half rho V2 square minus V1 square. Okay. Now H1 minus H2 is almost the difference of these two heights. Let us consider that H. So difference of height for this portion is considered to be H. So we can write, cancelling rho, that GH, rather 2GH equal to V2 square minus V1 square. V2 square minus V1 square. What we have to find? V2. Now let us consider the equation of continuity at this stage. What equation of continuity will give? It will give us A1 V1 equal to A2 V2. A1 V1 equal to A2 V2. Then we can also write from this that V1 will be equal to A2 V2 by A1. Substitute it here in place of V1. What you will get? V2 square minus A2 square V2 square by A1 square. Okay. 2GH equal to V2 square minus A2 square V2 square by A1 square. Done. Now 2GH, V square common, V2 square common, we can write it is equal to 1 minus it is coming A2 square minus A1 square. Fine. Then what about V2? V2 is coming 2GH divided by 1 minus A2 square by A1 square. This thing, this entire thing is divided here, and I take the square root, then it will be root over of 2GH divided by 1 minus A2 square minus A2 square divided by A1 square. This is the general form to find the V2 coming out from the bottom of the tank, velocity of water coming out from the bottom of the tank. Now First complete this one. Is it clear? The direct application of the Bernoulli's theorem will give you this result to calculate the velocity of the water coming out from a hole at the bottom of the tank. Now we will see some interesting cases. PA, a tank, water tank, suppose. What can be its maximum height from the top and bottom? How much possible? Any tank prepared? How much? 5 meter top to bottom. So with that 5 meter distance, will the atmospheric pressure change too much? No. So if you are at the ground floor of a building and you are going to the top floor, you will say that atmospheric pressure is changing by appreciable amount. Is it true? No, because atmospheric pressure can change if you are moving to say Ladakh. Then atmospheric pressure changes appreciable amount. Then you have to consider that there is a too much change in atmosphere. You are going to Sikkim Gurudammar Lake. That is almost 8,000 feet, close to 8,000 feet height. So in that case, the atmospheric pressure will change too much. But for the length of the tank, atmospheric pressure will not change that much amount. It is not its change is not appreciable. So we consider P1 is exposed to air, P2 is both the ends are exposed to air. So P1 and P2 both are equal to atmospheric pressure. Okay. Now, after this, if I consider the opening of the tank is too large and the hole prepared at the bottom is too small, just like a pinhole, very small. Okay. So in that case, can I write that A2 by A1, this term is very less than 1. Suppose the normal tank that is used, this much wide opening, but the pipe through which the water is coming out at the bottom, this pipe is very small area. So we can consider that A2 is very less than 1. In that case, A2 square by A1 square, I can consider it is almost tends to 0 because it is much smaller. If A2 by A1 suppose 1 by 100, then A2 square by A1 square will be equal to 1 by 100 square. So it is negligible, right? If you find the ratio A2 by A1 is 1 by 100, then A2 square by A1 square, this result will be 1 by 100 square. So that is very negligible. So we will neglect it and see after neglecting what you get. V2 equal to root over of 2GH. You earlier get this result. You earlier got this result in kinematics, motion under gravity. Suppose an object is taken to a height h and then released. So what will be its velocity of free fall when it is close to the ground? Root 2 gh. The same velocity will come as if the water from this point is freely falling and ejecting from this, and this water will come out with a very high velocity. Once this pinhole is opened, water will rush outside. This velocity is called the Torricelli's efflux velocity. EFFLUX. Torricelli's efflux velocity. Efflux means outburst. So as soon as this whole pinhole is closed, now suppose pinhole is open for a tank, with very huge speed the water will come out. So that's why it is termed as efflux velocity. So efflux velocity is similar to the velocity of a free fall ring body from a height h. This is the general form. A2 টা efflux হতে গেলে কি করতে হবে? A2 should be very very less than A1. Otherwise the efflux হবে না. Efflux মানে কি? Tank is filled and now from the bottom portion there is a pinhole. Suddenly pinhole mouth is open. Water is rushing with a high speed. That is called efflux. Okay? This is between conduction and convection. No? No medium. So okay, convection current forms in air. So you are not considering air as a medium. What is the difference between conduction and convection? Achha, I will give you one example, very common example. Suppose there is some book kept on the table. I supply the first book to him, then another book to him, then another book to him, and as a result he is transferring the book to you, then that book is transferred by you, that book is transferred by you. So book from this portion is transferred to the last person of this row, but none of your position is changed. What you are doing? What are the movement of your hands? You are receiving it from me and transfer it to the next one. Receiving it from me, transfer it to next one. So what is the motion of your hand? It's like oscillation, and we can consider at this initial level that this oscillation is simple harmonic. It is not simple harmonic actually, but still we will consider as an ideal case that is oscillation is simple harmonic. So now what is moving simple harmonically in case of heat transfer process? The molecules. So whenever heat is given, the vibrational kinetic energy of the molecules will increase. This molecule will start to vibrate. That is, your hand is moving here and there. It is comparable to the vibration of the molecules. From this one you are receiving heat, transferring to the next one, receiving it, transferring to next one. But your average position or mean position is not changed. So that is called the conduction of heat. So in this way heat energy is transferred from one portion to another portion without any noticeable displacement of the molecules of the medium. Molecules of the medium are only vibrating, so their average displacement is 0, but heat is transferred. This kind mechanism of heat transfer is called conduction of heat. Clear? Now think about a different situation. Students are collecting the books. First one collecting the book and going to the last bench, because she comes in the first bench, then you comes to the second bench, then you comes to the third bench, and again she is receiving the book, she is going to the last bench. So you are now, the third one is now on the first bench, moving one by one. So one by one collecting the book and going at the back. So when the entire motion is complete, again he is coming in the first bench. So this is the movement of the molecules is seen. So this molecule is actually moving, receiving the heat and going to the farthest end. That second molecule receiving the heat, it will go to the farthest end. So in this way what happens actually? Suppose this is a water in a container. The bottom layer's molecule will receive the heat from first, then they are heated up. Heated up means they are lighter. So they are moving upward, and cold and dense layer will come down. Then that layer will receive heat and this will follow this one, go to the top. The next layer comes down. Next layer receives the heat, it will become hotter, moves following the first two, and in this way there is a movement of the molecule, and as a result hotter molecules are moving up and transferring the heat energy with it up to that top. Okay. So this method, there is a molecular motion involved for the heat transfer. This is called convection. In conduction, molecules are not moving from their mean position. In this case, molecules are truly moving from one portion to another portion. That's why it is named as convection. And since they are moving, we call it convection current. Clear? Now, in solid material, which process you can see? Conduction or convection? Conduction, because solids molecules are rigidly fixed at its position. They are not changing its position. In liquids, you will see convection. Okay. See this one. Suppose this is a lake filled with water, and in the daytime, during the scorching heat of the sun, up to a certain depth of water will be heated up. Water will be heated up. Then suppose up to this depth of the water is heated up. Then in which process heat is moving inside the liquid, this water? Conduction or convection? Radiation is other part. That is when coming to the great distance from the sun, then it is radiating. Then you can consider it reaches to the top surface. Then heat is transferred to this. So in which method heat is transferred? Inside the water. Conduction or convection? Earlier you said that for liquid, convection is the process. Now you cannot say convection now, because top surface receives the heat energy from the sun first. So it is already hotter and lighter. So it will not go down, it will stay at the top. Then its vibrational kinetic energy will increase. As a result, it will transfer the heat energy to the next layer. It will transfer the heat energy to the next layer. Then up to a certain depth, heat is transmitted. But this is due to conduction, not by convection. So convection is the dominating process in liquid, but not the only process. Whenever heat is supplied from the bottom, then you can see that it is convection. But here the heat is supplied from the top. So you have to remember that top layer is receiving heat energy first. So it is the hotter layer, it will not go down. And convection current will not form in this case. So everywhere you see the liquid and it is heated up, you cannot claim that convection current forms. This is the example of heat is transmitted through the liquid by conduction method. Okay. Now we will discuss the conduction method in detail. First one, we consider a solid object. This kind of a solid object we are considering. Now we consider that two ends of the solid are at different temperature. Means this surface suppose have a temperature of T2 or T1. This surface is at a temperature of T2, and we consider T1 is greater than T2. T1 greater than T2. Now, if T1 is greater than T2, then heat energy will flow from this surface to that surface, high temperature to low temperature. So we are considering that Q amount of heat energy is transferring in time t second. In time t, Q amount of heat energy is transferred between these two surfaces whose temperature difference is T1 minus T2, right? Then we also consider that each surface, these two perpendicular surfaces have the area of cross section capital A. Area of cross section capital A, and distance between these two perpendicular surfaces is say x, or you can also consider as L. So better to write it as L. L. Distance between these two perpendicular surfaces is considered as L. Okay. Then the rate of heat flow, that is Q by T, that is proportional to T1 minus T2, that is proportional to, and that is inversely proportional to length. Rate of heat flow is directly proportional to the temperature difference, directly proportional to the area of cross section of these two perpendicular surfaces, and inversely proportional to the length between these perpendicular surfaces. Okay, then we can define a constant K and write this one as Q by T. It is equal to K A T1 minus T2 divided by L. Q by T equal to K A T1 minus T2 divided by L. Okay, this constant K is called the thermal conductivity. Thermal conductivity, ITH. Alright, I thermal. Okay, then compare with Ohm's law. Why electric current flows? Due to the electrical potential difference. So in this case, thermal current will flow for thermal potential difference. Thermal potential difference means difference of temperature. So T1 minus T2 can be considered as thermal potential difference or thermal voltage. So you can write this one as V thermal. Then write this term as K by L by Ka. This Ka is taken L by Ka in the denominator. Then compare with Ohm law. I equal to V by R. So this quantity in the denominator is equivalent to resistance, here called the thermal resistance. So that is R thermal is equal to L by Ka. L by Ka. Okay. Where K is the thermal conductivity. Thermal conductivity of the material. And see the analogy with the electrical resistance. We know that electrical resistance can be written as R equal to rho L by A, where you call rho as the resistivity of the electrical resistivity of the material, L is its length, A is area of cross section. See, the same thing comes. K is conductivity, so 1 by K will become thermal resistivity, directly proportional to L, inversely proportional to area of cross section. So it has the same format as that of the electrical resistance and same property as that of the electrical resistance. It is directly electrical resistance is also directly proportional to length if area of cross section is constant. So similarly, thermal resistance is directly proportional to length if area is constant and inversely proportional to the area of cross section, like the electrical resistance. Okay. How I equal to? Oh, this one, Q by T is considered as thermal current, then T2 minus T1 is considered as thermal potential difference, then there is Ka in the numerator. So if you write it in the denominator, it will be L divided by K, then I equal to V by R. So compare with this one as R, Ohm's law, I equal to V by R. So compare it with that Ohm's law. Then this quantity will become thermal resistance of the material. How is not? We considered that because in case of potential difference V, you write V1 minus V2 is the potential difference. So here, due to electrical potential difference, electric current flow. Due to thermal potential difference, heat will flow. So that's why T2 minus T1 is considered as the thermal potential difference. Okay. Now, what about the calculation of the conductivity? See, resistance and the conductivity, this quantity are inversely related in this equation. If I consider the other quantities L, A, all these things are constant. So combination of resistance will follow certain rule, you know, that is series combination, it will be sum, parallel combination, it will be the sum of the reciprocals. So conductivity will follow just the opposite rule. In series combination, it will be the sum of the reciprocal. In parallel combination, it will be only sum. Okay. Now, we will discuss two particular conditions of the heat conduction. One is considered as the variable state, other is considered as the steady state. Can you tell me in this case which state is considered, steady state or variable state? Steady state or variable state? What is the difference between these two terms? See, if I consider this one is divided into many parts. Okay, I consider the temperature T1, then in any other case I will consider this surface is at temperature T1, suppose this is at temperature say T2, then in between T3, T4, T5, T5 like this, and finally we consider some Tn starting from T1 up to Tn. Then when you start the delivering heat, transferring heat from this first surface, it will be at the highest temperature. As you are going to that opposite end, the temperature of each and every segment will decrease, and as a result there is a decrease in temperature, so heat will flow from one segment to other segment, then other segment, other and so on. This is the process. Now during this process every segment is receiving heat energy. So initially let us consider entire chunk is at temperature say 0 degree Celsius. Now this portion temperature will increase faster because it is directly receiving heat energy from the source. The next portion receiving heat energy from the previous one, so its temperature will rise, but rise is not that much huge, okay, but it will rise. Now one time will, so as soon as every segment is receiving heat energy, its temperature is going to rise, but it is always less than the temperature of the previous segment, and always it has the temperature greater than the upcoming segment, okay. So that's why heat is flowing from this end to that end. Now this situation where the temperature of every segment rises, that is called the variable state. Heat is transferring from one layer to another layer, but temperatures of each layer is increasing. That is called the variable state, okay. Now initially everything is at 0 temperature, now it is increased, it is also increased, it is increased. Suppose it will reach to the 50 degree Celsius, second one 48 degree Celsius, third one 46 degree Celsius, then 44 degree Celsius, and so on. So every temperature, as soon as the heat is supplied, temperature is going to increase, but the slope is always there, like this. This cannot increase further. So this side will be maximum, then further increase, all are increasing. When the temperature of every segment is increasing on receiving heat energy, this is called the variable state, and the calculations that we have done is not in variable state. This is after achieving the steady state. What do we mean by steady state? Suppose a particular temperature is reached. After that, whatever heat energy you will give, the temperature of the particular segment will not change. Temperature of a particular segment will not change. Means if it is 50, it will remain 50. Next one is 48, next one is 46, next one is 44. It will remain same, all will remain same. Only the heat energy received will be transmitted to the next portion. Then it is called the steady state. Whatever heat energy a segment will receive, it will transmit the entire heat energy to the next section without any increase in further temperature. Without any further increase in temperature, it will just transmit the heat energy to the next segment. There is some radiation, but temperature will not change at every segment. Then it is called the steady state, and this calculation is done for the steady state. Why? Because I consider here is T1, I consider this segment is at T2 and heat is transferring. Then after transmitting heat for time T, so time T can be divided into very small intervals, 1 second, 1 second, 1 second. Suppose it is 20 seconds. So it is divided into 20 parts of 1 second. Then after 1 second, whatever be the heat energy received, if this temperature changes from T2, then how can we calculate? So we are considering that during this time, the temperature of the two segments will remain same. So entire heat energy we can consider to be transferred to the next layer. That is called the steady state. Okay. Now, suppose this material is given. area of cross section, there are two different material cylinder, different metallic cylinders. I consider this one is of conductivity K1, this one is of conductivity K2. Their lengths are L1 and L2, different. Conductivities are different and only area of cross section is constant. Area of cross section is same. They are joined together. This side is kept at temperature T1, this side is kept at temperature T2, and they are already achieving steady state. Then what it is given that T1 greater than T2, then what will be the temperature of the junction? What will be the temperature of the junction that you have to find? Okay, this is the temperature of the junction that we have to find. Now check what is the rate of heat flow between this first junction and this intermediate portion. That we can calculate by using this formula, that T1 minus T divided by L1 divided by K1A, that is the rate of heat flow, that is Q by T. Q by T is this one. Check, difference of temperature divided by thermal resistance, that is the thermal current. Rate of heat flow means thermal current. So thermal current equal to thermal temperature difference, thermal voltage difference, voltage divided by thermal resistance. So I write this one. Now I equate this one with the second one, that is T minus T2 divided by L by L2 by K2A. So that is the thermal current for this part. Temperature T, it is going from, thermal current is going from T to T2. So that is thermal potential difference T minus T2 divided by thermal resistance. And I consider both the thermal currents are equal because they are connected in series. So whatever be the thermal current passing through this first conductor, the same current will pass through the second conductor. So they are connected in series. Okay. Now from this we have to find the expression for T. So this is the technique to calculate the junction temperature. From this you have to find the expression for capital T, that is considered as the junction temperature. Since they are connected in series, means the same thermal current will flow. Okay. Now, how to find the equivalent conductivity of this combination? How to find the equivalent conductivity of this combination? What are you trying? Break this one. How to find the equivalent conductivity for this slab? Combination of this slab, what will be the equivalent conductivity? Now consider this one is a single slab having length L1 plus L2 and having area of cross section same A. Okay. Equivalent means we have to replace them by a single one. So we consider that there is a single slab of total length L1 plus L2, area of cross section A, and that single slab has conductivity K, that is called the K equivalent for these two. Means same thermal current will flow through that slab, then it is called the series equivalent of these two. Then we can write for that particular slab, it will become T1 minus T2 divided by L1 plus L2 divided by Ka, that is called equivalent, K equivalent by into A. We consider that if this two slab is replaced by a single slab having conductivity K equivalent and have the same length L1 plus L2 and area of cross section same, then through this single slab same current will flow when kept under same temperature difference, that is T1 minus T2. Then thermal current for that single slab, equivalent slab, will be T1 minus T2 divided by L1 plus L2, that is total length, divided by K equivalent into A. Then we have to find the expression for K equivalent, that is called the equivalent conductivity. Okay. First see this one. We consider these two are connected in series because same thermal current will flow through each of them. So we consider that this one are equal. Now we consider that a single slab is taken having length L1 plus L2 and having the same area of cross section, whose conductivity will be K equivalent such that this single slab, through this single slab same amount of thermal current will flow when the two ends of the slab is kept between the potential difference T1 minus T2. So then we can write the same current is there. So this is the expression for the current. So we write T1 minus T2 divided by total length of the new slab divided by K equivalent into A. Then how to calculate? You have to calculate K equivalent from this. See, previously when these two are given, you are instructed to calculate junction temperature T. Now junction temperature T's expression is with you. Now if you consider these two, then by eliminating T with that expression you can find, but it will be a very long calculation. So we want to bypass this long calculation. How? I can write this one as T1 minus T2 divided by L1 plus L2 divided by K equivalent into A. This is simply equal to T1 minus T2 divided by L1 by K1A plus L2 by K2A. What I have done, this side remains same. On this side I take the sum of these two, numerator plus numerator, denominator plus denominator. Numerator plus denominator, minus T plus T will cancel, it will become T1 minus T2. Denominator added. Now this method is called like that. I have done this one. A by B equal to C by D is there. I write each of them equal to A plus C divided by B plus D. This is called addendo. There is a technique of algebra that is called addendo. There are other methods that you have learned, I think, in while you are solving the problems of trigonometry or ratio proportion in algebra in class 8 or 9, componendo and dividendo. How many of you know this one? This addendo, componendo, dividendo, all these things. These are in algebra class 8 or 9, I think. So this technique is called the addendo technique. So that I have used to simplify the calculation. Otherwise, you have to find out the t, then you have to substitute this t here, then you have to do the long calculation to eliminating t. So it will take one page long calculation. So use this addendo directly. So if the ratios are given like this, a by b equal to c by d, then each of the ratio is equal to sum of the numerators by sum of the denominators. That is a plus c divided by b plus d. This technique is called addendo. This is the name, a addendo technique. And if it is given a by b equal to c by d, you can also write this one as a plus b by a minus b equal to c plus d by c minus d. This is called componendo and dividendo. Componendo, dividendo. First one is addendo, second one is componendo and dividendo. Okay. Now from this T1 minus T2 can be cancelled. Simply I can cancel this one. Means I am just writing this one as K equivalent by L1 plus L2. Then this L1 plus L2 is multiplied on this side and you will get this form. K equivalent will be equal to L1 plus L2 divided by K1, L1 by K1 plus L2 by K2. Okay. Now from this you can get your familiar formula. If we consider L1 and L2 both are same. Check what will happen if L1 and L2 both are same. Put them L. L1 equal to L, L2 is also L. Put them and find the conductivity, you will get the familiar formula. It will come 2 K1 K2 by K1 plus K2. That is the combination, series combination of conductivities. Series combination of conductivity. That formula will come if you put L1 equal to L and L2 equal to L. Because this one will become L1 plus S2 will become 2L, and there is L by K1 plus L by K2. Take L common and cancel. It will be 2 divided by 1 by K1 plus 1 by K2. That is 2 K1 K2 by K1 plus K2. That is the formula for series connection of conductivity. Because in series it is the sum of the reciprocals. So 2 K1 K2 by K1 plus K2 will come. In parallel it will be different. Okay. So always when you are trying to solve this one, this type of problem of conductivity, equivalent slab, everything, try to calculate the thermal current, not Q, because in that case it is very easier, because the conductivity will come in the denominator as if it is a thermal resistance, and then you can apply the technique of electricity directly to solve the problem. So that's why don't write Q equal to Ka T2 minus T1 divided by L into some time. Write it in the form Q by T, that is thermal current. radiation process. Radiation process does not require any media. When light is when heat is transferred in radiation process, it has the same speed as that of any electromagnetic wave in vacuum, that is 3 into 10 to the power 8 meter per second. Now this radiant heat, or when the radiation occurs from the surface of an object, this follows certain rule that you know. One is considered as the Stephen's law that you have already studied, another is Newton's laws of cooling. Mostly the question will come from these two. And initially when this was studied, then the rate of heat loss of a substance is measured. Suppose you have any spherical object or any other object, from its surface area heat is radiated. Okay. Now we consider initially the Newton's law of cooling. So Newton was the first one who predicted a law for specifying the rate of energy radiation from the surface of a body, and it is considered as dE dt, that is rate of heat loss, is directly proportional to the first power of temperature difference. Temperature difference between what? The body which is radiating heat and the surrounding temperature, their difference. Okay. So if the body which is radiating heat has temperature capital T, the surrounding has a temperature T naught, then difference of temperature will be T minus T naught. Then the rate of heat loss is directly proportional to T minus T naught, provided T minus T naught is very small. Provided T minus T naught is very small, then only this law will be true according to Newton. So now after radiating heat, the body will lose temperature, so it is cooling. So this is termed as Newton's law of cooling. So then to write this one in a form of an equation, we can write, or better not to write E, write Q, because you are familiar with this example in thermodynamics, that is Q is the heat. Now I can write it in the form of an equation, dQ dt equal to some constant k, small k I write, into T minus T naught. There should be a minus sign because the body is losing heat and its temperature will decrease. So on radiating heat, temperature will decrease. So that's why this minus sign will come. Okay. So that is called the rate of heat loss by a body. Now you know that this dQ can be written as ms in m into c into dt, because you have already studied this law. dQ equal to m c dt. Sometimes you write ms dt, that is specific heat capacity, but since in thermodynamics we use the term CPCV, that's why I write C. Now we are talking about the heat loss process by a solid body, or a solid, mostly by a solid body. So then Cp and Cv are not different, so we will consider only C, not write any suffix. Then if I substitute this one, this will give you a equation mc dt, that is equal to minus small k into T minus T naught. Then we can write this one as dt by dt, that is ddt of capital T, this is equal to minus some constant capital K into T minus T naught, where we consider that capital K, this one is small k divided by mc. This entire thing is considered as a constant. This C is the specific heat capacity. Sometimes you can write it also S, but since I used in thermodynamics CPCB, that's why I write C. Okay, so this is the rate of decrease in temperature. That is also directly proportional to difference of temperature T minus T0 between the body and the surrounding when difference of temperature is low. It is termed as Newton's law of cooling. Now, how to find the final temperature of a body after certain time? If the temperature now is Ti, suppose, what will be the final temperature at a later time? Okay, so for that I can write this one as dt by T minus T naught integrated from Ti to Tf, that is initial temperature to final temperature, initial temperature to final temperature, that is equal to minus k into dt integrated from initial time to final time, means 0 to t. So suppose the temperature of a body now is temperature of the surface temperature of a body is now Ti. After certain time t, what will be its surface temperature if it is losing heat, then if it is radiating heat. So in that case you have to do this integral to find expression for Tf, that is the final temperature after a certain time, if initial temperature is known and all this quantities k constant is known. Then we can write from this after integrating that it is log of T minus T naught, limit is from Ti to Tf, that is equal to minus kT, that will be equal to minus kT dt by T minus T0, its its integration will be log of T minus T0, where this log means the natural log, means base is e, not 10. Then you can write this one as log of Tf minus T naught divided by Tf Ti minus T naught equal to minus kT. How? Putting the upper limit, it will be log of Tf minus T naught minus log of Ti minus T naught, then log A minus log B will be log A by B. I have written it directly, log Tf minus T naught by Ti minus T naught. Okay, this one. Then Tf minus T naught by Ti minus T naught is equal to e to the power minus kT. E to the power minus kT. So remember this form. There is one question in your one of the mock paper, that is after 10 seconds this will be the temperature, then in 10 minutes, then in the next 10 minutes, after next 10 minutes what will be the temperature of the body. So if you start from this step, you can solve it very easily. So this type, for this Newton's law of cooling, don't start to write from this one, because in that case you have to derive the entire formula and then go for the problem solving. So remember that formula, final formula, and whenever the problem will come, apply that and calculate. Okay. Now, what will be the final temperature of any object which is radiating heat in a where the surrounding temperature is T naught. The surrounding temperature T0 or T naught, the temperature of the body is Ti initially, it is radiating heat. So what will be its final temperature after a very long time? After a very long time, not 10 seconds, not 20 seconds, after a very long time, what will be the temperature of the body? Temperature of that radiating surface, where surrounding temperature is considered as T naught and initial temperature is considered higher than that Ti. Now it is radiating. Suppose surrounding temperature is 20 degrees Celsius and body is initially at 100 degrees Celsius. Now it is radiating, then after a very long time, what will be the temperature of the body? Equal to the surrounding temperature. It will be equal to the surrounding temperature, because the body cannot be cooled beyond the surrounding temperature. So surrounding is at 20 degrees Celsius, from 100 degrees Celsius it is cooling. So you can consider the final temperature of the body will become T naught only. Now here you will say that after losing the heat energy, surrounding will receive that heat energy, its temperature will increase. So let us consider a cup of tea. It is losing heat energy. Okay, suppose the temperature of the tea is initially, suppose 90 degrees Celsius and surrounding atmosphere is the temperature of our atmosphere is 30 degrees Celsius. Now you are claiming that when my tea will be cooled down, the temperature of the atmosphere will increase. Is it possible? Because atmosphere is a vast ocean, like heat reservoir. So some heat is taken from it, some heat is given to it. That does not mean anything. There will be no change in its temperature. So a body cannot be cooled beyond its surrounding in a natural process. Only it can be cooled beyond its surrounding if and only if reversed heat engine can be used, otherwise not possible. So how can you prove this one? From this step only. Very long time means small t tends to infinity, so e to the power minus infinity, this tends to 0. This side will be 0, then this term multiplied with 0 will be 0. So Tf minus T0 equal to 0. So what will be the value of Tf? T0. So it cannot be cooled beyond the temperature of the surrounding by this process. Clear? Is it clear why it cannot be cooled beyond the temperature of the surrounding? Because if you put T tends to infinity after a very long time, then this term will be 0. Then T minus T0 will be 0 and Tf minus T0 equal to 0. So Tf should be equal to T0. So it cannot be cooled beyond the surrounding temperature on its own. You have to apply refrigerator and all these things to do this. Okay, so this one is Newton's law of cooling. This is only valid if this difference of temperature is very small. If this difference of temperature is very large, then we cannot apply this one. Then the correction comes with Stefan's law. Stefan's law. In Stefan's law, you will find that this rate of heat loss, that is proportional to T to the power 4. Rate of heat loss that is proportional to temperature to the power 4. This is called the Stefan's law. Now there is a Boltzmann correction of the law which is named as the Stefan-Boltzmann law. Then it will be dq dt proportional to T to the power 4 minus T naught to the power 4. Because Stefan's law is initially predicting the correct result, but irrespective of the surrounding temperature. But Boltzmann corrected the law by saying that the radiation from a body is not only depend on its surface temperature only, it will also depend on the temperature of the surrounding. So you cannot ignore the surrounding temperature's effect. So that's why T4 minus T0 to the power 4. That is the Boltzmann correction of the Stefan's law. So first one is called only Stefan's law. Second one is called Stefan-Boltzmann law. Okay. Now, if you consider either of this law, then you can write that dq dt is equal to some constant will be there. That constant considered as, since it is cooling, I put the minus sign, some k, but this constant also containing the term of surface area, because the heat is radiating from surface area. So if the surface area more, the heat radiation will be more. Suppose you have a cup of tea, it is very hot. Some people used to pour the tea over a plate such that it will be cooled down faster, because the surface area increases, so radiation will be at a faster rate, then it will cool down quickly. So that's why this area term will come here. It will be T to the power 4 minus T naught to the power 4. Normally it is not written as K, it is written as sigma, called the Stefan's constant. Sigma A T to the power 4 minus T naught to the power 4. This sigma also contains the term emissivity from a surface, because different surface have different emissivity. Suppose you have a two sphere identical, one made of iron, one made of aluminium, both will not radiate heat at the same rate. So it is a property of the material, that is called the emissivity. Okay, so there is another question that comes in your mock paper. For its solving, it is required that the rate of heat loss that is to be calculated, heat radiated. So it is actually the power. Rate of heat loss. Rate of heat loss means power radiated. So you can write this one as P or E, then it can write be P1 by P2, and with context to this one it can be written as A to the power A1 by A2 into T to the power 4 minus T naught by T2 to the power 4 minus T naught to the power 4. And the law is given by considering this initials irrespective of the surrounding temperature that has to be calculated, that is in the question. So T naught you can put to be 0 for the calculation, since it is given that the radiation is considered irrespective of the surrounding temperature, that is in the question. So you can skip this term and write this one as T1 to the power 4 by T2 to the power 4. But actual law is T naught to the power 4 has to be subtracted. No, that question is T1 to the power 4 minus T naught to the power 4 divided by T2 to the power 4 minus T naught to the power 4. But in the question it is given, it is irrespective of the surrounding temperature. So Boltzmann correction is not required. We have to start with the Stefan's law and find the answer. And one thing is that from Stefan's Boltzmann law, you can actually derive Newton's law of cooling. From Stefan's Boltzmann law, Newton's law of cooling can be defined, because Newton's law of cooling is an approximation case of the Stefan's Boltzmann law. because that is only valid for small temperature, and this is valid for all such temperature difference. You can consider this one, this Stefan-Boltzmann law. So if you start from the Stefan-Boltzmann law, this one, you can write this one as dq dt equal to minus sigma a t square plus t naught square into t plus t naught into t minus t naught. Check whether it is coming or not. T square whole square minus t naught square whole square. It can be written as t square plus t naught square into t square minus t naught square. Then t square minus t naught square is split it further. That is t plus t naught into t minus t naught. Now consider t minus t naught is very small. Very small. This difference is very small. That means we can almost consider t equal to t naught. When these squares will come and addition will come, okay, then since the difference is only very small, so we can keep this term, and remaining term we can put t is almost equal to t naught. Then this one will become dq dt equal to minus sigma a. This one will be 2 t naught square, then it will be 2 t naught into t minus t naught. I will consider only t minus t naught as an appreciable amount, and then where there is t plus t naught or t square plus t naught square, in each those terms we put t equal to t naught, because t and t naught are very close. Only first order approximation is taken. First order is taken. Then this one will become dq dt equal to minus 4 t naught cube sigma a into t minus t naught. It is coming dq dt equal to minus 4 t naught cube sigma a into t minus t naught. Now t naught is the surrounding temperature, so that is constant. So write this entire thing constant. So write this entire thing as constant, and then you will get dq dt equal to minus some constant k into t minus t naught, which is Newton's law of cooling. Okay, so Newton's laws of cooling can be directly derived from Stefan-Boltzmann law, because that is the generalized law. This is the ceiling from which there is a rod and connected with a fixed pulley wheel. A string is, inextensible string is passing over this pulley wheel like this. There is a mass 5 kg. There is another mass 3 kg. Okay, string is inextensible. Find the acceleration of the masses. Find the acceleration of the masses. This one is fixed, this side mass is 5 kg, this side mass is 3 kg, this one is released. g by 4. Just calculate what is the acceleration of the masses. G is given 10. It is coming g by 4. How it comes? Complete the free body diagram first. meter per second square. G is given 10. So it is coming 2.5 meter per second square. How? First, we have to complete this free body diagram. That is, consider this mass as M1. So it will be M1G in the downward direction. This one is M2G weight in the downward direction. Tension T, tension T. This mass is heavier, so moving down. This mass is lighter, so moving up with same acceleration. Because string is given inextensible. Since the string is inextensible, we can write this one. So now we write the equation of motion. I will show you the formal technique once. That is, this mass is moving down. So downward force must be greater than the upward force. So resultant force will be M1G minus T. That will be equal to M1A. M1G minus T equal to M1A. Okay. Now for this second mass, upward force is greater than downward force because acceleration is in the upward direction. So we write T minus M2G equal to M2A. Now add these two, tension will cancel. You can write M1 minus M2 into G will be equal to M1 plus M2 into A. And from this, A can be written as M1 minus M2 by M1 plus M2 into G. Now M1 is 5, M2 is 3. So 5 minus 2, 5 minus 3, that is 2, and 5 plus 3, that is 8. So it will be 4. So G by 4, G is given 10. So it is 10 by 4. That is 5 by 2 meter per second square. Okay. Is it clear to all of you? This is not the question what we are going to discuss. This is the introduction. The question is this one. See, I have shown you this. This calculation is given such that when you are calculating the acceleration, you can use this value directly for this particular problem. So that's why I said to calculate this acceleration. The problem is this one. See, same setup, 5 kg and 3 kg are there, and it is said that this is the ground, and by applying a force by your hand, you put this mass over the ground. Okay, you are holding this mass at the ground by your hand. That's why this mass is hanging in air. Then it is given that the position of this mass above the ground is 4 meters, suppose. Position of this mass above the ground is 4 meters when this 3 kg mass is standing on the ground. You hold it. Now you release this. What will happen? This mass will move up and this mass will go down. Is it clear? Then write down the question. Find the maximum height reached by the 3 kg mass. Find the maximum height reached by the 3 kg mass above the ground. When it is released, find the maximum height reached by the 3 kg mass above the ground when it is released. How much will it release? Will it rise above the ground? The 3 kg mass. I asked you to calculate the acceleration previously because that acceleration is required for the calculation. That's why I have given that. What your common sense will tell you, how much it should rise. Will it be equal to 4 meter? Will it be less than 4 meter or more than 4 meter? First, tell me this one. The 3 kg mass when released, it will reach up to a certain height. Will that height be equal to 4 meter? Greater than 4 meter or less than 4 meter? This will be greater than 4 meter. Maximum height reached by the 3 kg mass above the ground is greater than 4 meter. Why? See what will happen. This 5 kg mass will move down. How much it will move down when collide with the ground? 4 meter. So the length of the string on this side increases by 4 meter. So this mass should increase by 4 meter. That is for sure. 4 meter it will rise. Now what is its initial velocity? 0. So when it will rise to the 4 meter, suppose at this position, it has some velocity in the upward direction. Write it as V1. Here U is considered as 0. How much it will rise? Say H1. H1 is 4 meter up to this. Okay. Then calculate this velocity. We can write this is final velocity, so V1 square. That is initial velocity 0. So it will be 2. With which acceleration it is moving up? A, 5 by 2. So 2 into acceleration into H1, that is 4. So V1 equal to root 20 meter per second. Root 20 meter per second. So will this 3 kg mass stop here or it will rise further? It has the velocity. so it will rise further. So its height reached will be more than 4 meter. Okay, so how long it will rise? Until its velocity will become 0. So this mass will rise up to certain height, say this much, until its velocity will become 0. Now here velocity is root 20, here it is 0. Then how velocity can decrease? Only if there is some retardation. Is it retarding or it is accelerating? No, its acceleration comes to an end, this 5 by 2, because when it will reach to the 4 meter, this mass comes to the ground. It cannot go further, and this, due to this velocity, this mass has a tendency to move up. The string is no more taut. Only a taut string can, or only a stretched string can exert tension. If the string is unstretched, string cannot give tension force. So since it is moving up, the string is now this much. So this string cannot exert tension. And if the tension is not given, this mass in this position is moving under only gravitational force. Gravity is in which direction? So it is just like some particle is thrown with a velocity v1 upward. Due to gravity, at a certain distance its velocity will become 0 and then it will fall. So this is now moving with retardation, and retardation is created by gravity alone, because up to 4 meter this acceleration is present, but once it reaches the 4 meter it will go further. As soon as it will go further, string is no more stretched, and unstretched string cannot apply tension force. Unstretched string cannot apply tension force. So if the tension is absent, then only gravitational force will act on it, and gravitational force is downward and velocity is upward. So this is behaving like retardation, and this velocity will become 0 after a certain height. Okay. Then next part of the problem, consider the final velocity 0, initial velocity root 20, its square minus 2 into acceleration due to gravity, g into further height is considered as h2. Suppose this much height is considered as h2. Okay, in that case g you have to say v square equal to u square minus 2gh now. So it is coming 20h2 equal to 20. So h2 will be equal to 1 meter. So how much it will rise above the ground? 4 meter plus 1 meter, that is 5 meter. So maximum height reached above the ground is not 4, it is more than 4, that is 5 meter. Because it will rise up to this, and at this moment it has the velocity, so it has the tendency to go up. Until its velocity is 0, it will not stop and fall down. So maximum height reached is not here. Up to a certain height it will reach. Here it is going with acceleration, but as soon as it rises 4 meter, mass goes to the ground and it is connected with the ground. This mass cannot go beyond, and as a result the length of the string is already here fixed. Now it is moving up. Since it is moving up, but this mass cannot go down further, so the length of the string is no more stretched. It is in unstretched condition. Unstretched condition means tension is not there. If the tension is not there, then that acceleration is absent. So then which force only acts on this mass? Only gravitational force, and gravitational force is downward, producing retardation. So that's why second part is the retardation under the action of gravity. So whenever this type of problem comes, this is a tricky problem. It is said that whether the maximum height achieved by the 3 kg mass will be equal to 4 meter, greater than 4 meter or less than 4 meter. This type of options are coming. So don't write it is going by the height of 4 meter only. It should be greater than 4 meter. So tick the correct option. That's why I show you the entire problem, why this happens. Okay. So if you have a concept over this thing, the entire calculation will not come in the NEET. Only require the basic concept. Basic concept is that as soon as it will reach the 4 meter, the string is no more stretched. So its acceleration is absent. Now due to that velocity, it will reach up to further height and until its velocity will become 0. And from that you can immediately predict then it will be more than 4 meter and choose the correct option. Okay. So on the conceptual background you can find the option which one is correct. Not the detailed solution is required. Okay. It is given that x1 equal to 3 sine omega t, another one x2 equal to 4 sine omega t plus pi by 2. These two are two simple harmonic motions, simple harmonic vibrations. These two will superpose on each other. Both are propagating, both are vibrating, and this will superpose on each other. Then what will be the amplitude of the resultant vibration? What will be the amplitude of the resultant vibration? Say this some unit is given, say centimeter, then resultant vibrations amplitude. This one, see, you can write this one as 4 cos omega t. Sine pi by 2 plus omega t. So it will be 4 cos omega t. Okay, because pi by 2 plus omega t, it is in second quadrant. Second quadrant sine is positive and odd multiple of pi by 2. That's why sine is converted to cos. Now check, these two are the simple harmonic vibrations. Then resultant vibration amplitude will be simply A equal to 3 square plus 4 square, its positive square root, means 5 centimeter. Only the individual amplitudes square, take the individual amplitude square, add them and take the square root. Then how it comes? Because any two simple harmonic vibrations, when superposed, the resultant vibration is also a simple harmonic vibration with different amplitude and different phase. Phase will be changed and amplitude will be changed, but the frequency will remain same. How can we find that? We have two vibrations now. One is x1, other is x2. Then I can write that in general, I can write this one if x1 equal to say a1 sine omega t, x2 equal to a2 cos omega t, like this, where a1 is 3 and a2 is 4. So I write the general form. Then you consider this one, x equal to x1 plus x2, that should be a1 sine omega t plus a2 cos omega t. Now in this case, how many constants you have? a1 and a2 as the amplitude. Now you consider it in a different manner. I will consider, let a1 equal to capital A cos phi and a2 equal to capital A sin phi. I will consider that. Now you are saying, why this particular shape? It may be any other shape. Okay, I consider that these are sinusoidal functions, so I consider them in a sinusoidal function. Only thing that you have to concern that the number of constants remain same or not. Previously it is a1 and a2, now it is capital A and phi. So previously there are two constants, now there are two constants. Okay, then substitute these two constants here. So first one will become capital A cos phi sin omega t plus capital A sin phi cos omega t. Then you can write x equal to capital A common sin omega t cos phi plus cos omega t sin phi, which can be written as x equal to A sin omega t plus phi. Check what we are considering: superposition of two simple harmonic vibrations. Their resultant vibrations is also a simple harmonic vibration with same frequency, different amplitude, different phase. So any combination of two simple harmonic motion is always a simple harmonic motion with different amplitude and different modified amplitude and modified phase. Clear? then what will be the amplitude of the resultant vibration? This capital A. So you have to find some way to find capital A. These two are there. Okay. Square them and add them. You will get the value of capital A. How? A1 square equal to A square cos square phi. A2 square equal to A square sin square phi. Add them. What you will get? A1 square plus A2 square. And this one will be A square only, because cos square phi plus sin square phi will be 1. So what is the magnitude, what is the amplitude? Positive square root. Root over of A1 square plus A2 square. That's why in this problem there is 3 and there is 4. I add the squares, sum, and then take the square root. So whenever two simple harmonic motions are given in this format, you can always do this technique by calculating the individual amplitude square, add them and take a square root. Elasticity in physics is completely different. Elasticity means the ability of a body to regain its configuration, means shape or size. So when you try to deform the object from its shape or size, if you try to alter this, the body which try to prevent it strongly is more elastic. Suppose there is a rubber band, by applying a small force you can change the shape of that rubber band. But if you have an iron rod and you apply same amount of force, you can do nothing. You have to apply more force to deform the iron rod. Means iron rod has more, iron will strongly counter any deformation which we try to impose on the iron material. Okay, so iron is more elastic than rubber. Clear? Now, there are two cases that we considered. First one, we apply the force on the rod to deform this or to change its length, anything. We apply the force, that is the applied force. Then as soon as you will apply the force, the material due to elastic property will try to counter this force by producing a elastic force or restoring force. It will try to oppose this, your applied force. Now suppose you deform the material by certain amount. Once the material is deformed, then only the elastic force will come, or when you start applying force, immediately the elastic force will come. When you completely deform the material, then elastic force produced, or when you start applying applied force, then only the elastic force is produced. Then only the elastic force will be produced. Now, two terms we will consider here. First one, to measure the deformation, it is called the strain. Strain, which is a measure of deformation of the object, that is strain. Second one is considered as stress. First one is strain, second one is stress. Strain means change in dimension by original dimension. Change in dimension of a body by original dimension. You can also consider it as the fractional change in dimension. Why I use this term dimension? It may be only change in length by original length, it may be change in volume by original volume. That's why I write change in dimension by original dimension. Okay. Then similarly, stress is elastic force produced per unit area to counter this deformation. Elastic force produced per unit area to counter this deformation is the stress. Okay. Now which comes first? Stress or strain? Once the body is strained, then only elastic force can come. If the body is not strained at all, then elastic force will not produce. So strain is more fundamental than stress. So strain will be produced first and then stress will be produced. Okay. Now according to Robert Hooke, stress strain, this ratio will be a constant, means stress is proportional to strain. As the body is strained more, the stress will be more. Okay, because stress comes due to the elastic force. So if you strain the body too much, the elastic force produced will be larger and stress will be larger. So according to Hooke's law, stress will be proportional to strain. So we can write stress to strain. This ratio is a constant. That ratio is called modulus of elasticity. Modulus of elasticity. Stress to strain ratio is a constant and that ratio is called modulus of elasticity. But think about a situation. Suppose there is a spring. You are stretching the spring will again come back to its natural length. You are stretching it further, it will again come back to the natural length. Now you are stretching it this much. Will it come back to the natural length? No. Means there is some permanent deformation. So in that case, this law is not valid. So that's why this stress to strain ratio is constant, means stress is proportional to strain, that is within a certain range. That range is called the elastic limit. So write down in the bracket, stress by strain ratio will be equal to modulus elasticity, but write in the bracket, within elastic limit this law is correct. You should not go beyond the elastic limit. This permanent deformation has a very good name. It is termed as the material is elastically fatigued. Material is elastically fatigued. How? Suppose you are said to go to your room and come back. You will go to the room and immediately coming back. Okay. You are said that next time you are said that you have to go to from this one to the SIRD written gate. You will go and come back. So this is your elastic limit. Now you are say, okay, by running you have to go to Shillong and then come back. Then after running, when you reach the Shillong, you will and immediately someone is with the car. No, you don't have to stop. Immediately you have to go back to the run again and go back to your hostel, such that showing that elastic limit is greater. You will say, I cannot. Take me some rest and after that I will go. So that is you are fatigued. So when you pull it this one, spring will again come back. When you pull this much, spring will again come back. You pull this much and release. Spring will come this much and stop. That is means it is elastically fatigued. So it is not coming back like that. You are, oh no, take me some rest and then I will go. The same thing. That's why the name is elastic fatigue. Okay. Now this stress to strain ratio is elastic modulus. Now we can define three types of elastic modulus. If the strain is produced along the length, means length is changed, because I consider that this strain is defined by change in dimension by original dimension. So first we define by change in length by original length. So that is considered as longitudinal stress by longitudinal strain. Huh?
Can I continue to explain?
Okay. Longitudinal stress by longitudinal strain. Okay. This is termed as Young's modulus. Longitudinal stress by longitudinal strain. That is the Young's modulus. Very young. Then we define one more, that is bulk modulus, B. Sometimes students write it as K also. Sometimes they are written B is this one and 1 by K is taken as the compressibility factor or many things. I write B. Bulk modulus, that is volume stress by volume strain. Volume stress by volume strain. Okay, that is considered as the bulk modulus. Then last one, N. Called the modulus of rigidity. Modulus of rigidity. Means shearing stress by shearing strain. Shearing stress by shearing strain. Okay, this is termed as modulus of rigidity. Now, if I consider a very long wire of length L, okay, now you are applying a force along its length, and due to this force an elastic force will generate to counter this one. We consider that has also the same value F. This area of cross section is considered as A, and this length is changed this much amount. This increase in length is considered as small l. Increase in length is considered as small l. Okay. Then you can write this Young's modulus equal to F by A, that is longitudinal elastic force per unit area. That's why it is termed as longitudinal stress. Means this force is along the length, divided by change in length by original length. That is the longitudinal strain. Strain has no unit or no dimension because it is the ratio of two similar quantities. But stress has the unit of pressure. Now, volume stress. Volume stress means, suppose there is a certain container inside a football, there is some gas, and football is tight. Means if you are applying a force on the any surface of the football, that is creating pressure, that is already the volume stress. So volume stress is itself the pressure applied. P divided by change in volume per unit volume. Change in volume is considered as delta V, but put a minus sign, because if pressure increases then volume will decrease. So that's why we have to put a minus sign before this bulk modulus. Okay. Now it is discussed for this initial volume. Now the shape is changed, so volume is decreased by an amount delta V and it is given some pressure. Now we consider the modulus of rigidity. Let us consider to measure the modulus of rigidity. See this one. It's this surface. It is a rectangle. I can apply a force on this like this, such that it will be almost parallelogram now, like this. This force is applied perpendicularly or tangentially? Tangentially, this much, like this. So this rectangle is now going to be a parallelogram. So by applying a force tangentially, so that is called the tangential stress or shearing stress. So we will draw this diagram here. So initially it's a rectangle. Now after applying a force tangentially, it will become like this. We consider, since it is a solid, very small amount of deformation will occur, and as a result this angle produced is theta. This angle by which it is slanting, it will become theta. Then consider this surface is AB, CD, then D is changed to D prime, C is changed to C prime. Due to this force, and this force is acting along this direction. And we consider the surface area of this over which this force is applied is capital A. So what is stress? F by A. But this is the tangential stress now. So that is termed as shearing stress. So shearing stress means tangential force per unit area. Now what is shearing strain? That we have to calculate. See, what will be the change in this dimension? C prime, and what is the initial length? This one, BC. So if I calculate C prime divided by BC, that will become tan theta. C prime divided by BC, that is the change in the length in the direction of the tangential force divided by this perpendicular length, that is BC. So C prime by BC, that is equal to tan theta for this diagram. Check. This is a right angle triangle at point C. This is theta. So this one is perpendicular, this side is base, and BC prime is the hypotenuse. So tan theta is perpendicular by base. So this is perpendicular, this one is base with respect to the angle theta. So we write C prime by BC equal to tan theta. Okay. Now tangential stress or shearing stress, all this time for solids. And is solid deformed by a very large amount? No. That means theta should be very small. Then if theta should be very small, then we know sin theta can be written as theta. Cos theta is 1. So tan theta will become theta, because tan theta equal to sin theta by cos theta. So for small theta, since it is defined for solid, I can write this is approximately equal to theta. Put it. Now check whether all strain is dimensionless. This theta is measured in radian, so that is also dimensionless. That is correct. Strain means change in any configuration by original configuration, so that is dimensionless. Change in length by original length, change in volume by original volume. So always strain is dimensionless. Same thing is maintained here. Theta means measured in radian, that is also dimensionless. So shearing strain is actually the angle of shear. Shearing strain is itself the angle of shear when measured in radian. And why we can consider that? Because theta is very small, because this shearing modulus of rigidity is only defined for solids. Rigidity, liquid and gas does not have the rigidity, only solid have the rigidity. Okay. Now we will discuss something more about Young's modulus. What we have ignored previously when we are defining Young's modulus is that the wear, if it is very thin, okay, then you can neglect when you are changing the length, there is a change in the diameter of the wear. Length is increasing, means total mass or volume remain constant, so diameter should decrease. Area of cross section will decrease, diameter should decrease, but we neglect that when we are defining the Young's modulus. But in the actual scenario, this wear is like a cylinder. Its length is suppose defined by L. Then you stretch this one up to this. So what will happen? So length is increased by a certain amount, and on the other hand diameter is going to decrease. So let us consider the previous length is L. The new length is defined as previous length is L, the new length is defined as L prime. New length is defined as, not the increase. I define here the new length is L prime. Similarly, I define the radius in the first case is small d, and diameter in the first case is small d. Diameter in the second case is changed to d prime. Initial length L, final length L prime. Initial diameter d, final diameter d prime. Okay. Then first calculate the longitudinal strain. Longitudinal strain. What will be that longitudinal strain? L prime minus L divided by L. Longitudinal strain. It is dimensionless. Now define another quantity. D prime minus D divided by D. That is the lateral strain. Lateral strain. That is final diameter minus initial diameter by initial diameter. So this should actually happen. Previously, when we consider a very thin wire, we neglect the lateral strain. But now in the general case when we are considering a cylindrical shape where area of cross section is not negligible in comparison to the length, then we have to consider that if there is an increase in length, there should be a decrease in diameter. You have to consider that. Now we can write this one as lateral longitudinal strain, and this one is defined as lateral strain. Remember, if longitudinal strain is positive, lateral strain should be negative. Means see, d prime is less than d, so it should be negative. And if the wire is compressed, then this one is negative, this one will be positive. So these two always have the opposite sign. Okay. Now we can define a ratio of lateral strain to longitudinal strain. Lateral strain by longitudinal strain, that is d prime minus d divided by d divided by L prime minus L divided by L with a minus sign, that is considered as sigma, called the Poisson's ratio. It is the ratio of lateral strain to longitudinal strain, that is termed as the Poisson's ratio. Minus sign is taken here to calculate it as a positive value, because lateral strain is itself opposite to the sign of the longitudinal strain. This one is termed as Poisson's ratio. It is the ratio of two strains. Remember, it is also dimensionless. It is not like elastic modulus, because elastic modulus have the dimension of pressure, because that is stress by strain. Strain is dimensionless, but the upper part stress is having the dimension of pressure. So Young's modulus, bulk modulus, modulus of rigidity all have the dimension of pressure. But this is not a dimensionless quantity, because it is the ratio of two strains. A strain is itself dimensionless. So Poisson's ratio is not a elastic modulus. Remember this one. Elastic modulus must be stress to strain ratio, and Poisson's ratio is strain to strain ratio. Okay. Write down one question. What is the Poisson's ratio for a cylinder of constant volume? What is the Poisson's ratio for a cylinder of constant volume? Option A 1, option B 0, option C half, option D 2. What is the value of Poisson's ratio for a cylinder of constant volume? cylinder, I can write pi r square L, that is equal to volume of the cylinder, where L is considered as the length of the cylinder, means height. R is the radius, then pi r square L is defined as the volume. Okay. Take logarithm on both sides. It will be log pi plus 2 log r plus log L equal to log V. Differentiate both sides. Differentiation of first term will be 0 since it's a constant. For second term it will be 2 dr by r. Change in diameter by original diameter. Instead of that I am calculating change in radius by original radius. That has the same value. So this is lateral strain. This one is change in length by original length. That is longitudinal strain. So lateral by strain by longitudinal strain with minus sign, that is Poisson's ratio. So sigma for a cylinder of constant volume will be plus half. And there are two formulas related to this one, Young's modulus. Remember this formula because sometimes directly by applying those formulas you can calculate the problem. One is this one, elastic potential energy per unit volume, energy stored per unit volume. The derivation is already in the book, that is half into stress into strain, or you can also write it in this format, half into Young's modulus into strain square. Either format can be used, half into stress into strain or half into Young's modulus into strain square, because if you are stretching a wire, then in the stretched wire some elastic potential energy will be stored. Okay. Then elastic potential energy per unit volume, that is elastic potential energy density. It is half stress into strain, or it can be measured by half into Young's modulus into strain square. These two proof are normally coming in the board exams. For this competitive exam, you remember this formula, and if the problem comes, directly put it and find the answer. Now tell me one question. Suppose there is a string connected from this end, from the ceiling, and at the bottom portion of the string a heavy load is hanged. So the string will be in stretched condition. Now suppose suddenly the string snaps. You are increasing the load, increasing further, it snaps. If you touch that snapped string, you will find that it is hotter. Its temperature will be more. Why? Whenever string snaps, you will find that its temperature will increase. Why? As soon as it snaps, its temperature will increase a little bit. See, whatever you have done previously, the string is hanging and from its lower end some heavy weight is hanged. So the string will be stretched, and stretched string means some elastic potential energy will be stored in it. Suddenly when it snaps, then this elastic potential energy will be converted to heat energy. So some portion of this elastic potential energy will now convert to the heat energy. As a result, the temperature of the string will increase. That's why snap string, it feels that it is hotter. Okay, because elastic potential energy is initially stored inside. Now it snaps, means this potential energy will not be stored inside, it will now convert to the other form of energy. So that's why a part of it will be converted to the heat energy, and that's why the temperature rises. Clear? One more problem. Suppose this one is a block. Okay. Block is kept over a horizontal surface. It is rough, having coefficient of friction mu equal to 0.6. Mu equal to 0.6. Mass of the block is given 5 kg. Let us consider this horizontal surface is the surface of a inside a moving truck. Inside the surface of a moving truck, this block is kept. Okay. The truck is initially at rest. The truck is initially at rest. It suddenly starts from rest with an acceleration in this direction, that is 5 meter per second square. It suddenly starts from rest with an acceleration 5 meter per second square. What will be the acceleration of the block with respect to the truck? What will be the acceleration of the block with respect to the truck? What will be the acceleration of the block with respect to the truck? the answer? Only 2 students have given the answer. As soon as the car starts, there is an acceleration of the entire system in the forward direction. So if we consider from the frame of the car itself, frame of the truck, that is an accelerating frame. In this accelerating frame, this object will feel the pseudo force. In which direction? In opposite direction to acceleration. So what will be that pseudo force? M into A. What will be its magnitude? 5 into 5, that is 25 Newton. Okay. Then in which direction friction force will act? In the front direction. Means due to this force, this block has a tendency to move on this side, so friction will try to oppose this. But what is the friction force? Calculate friction force. Mu A is given, coefficient of static friction is given, so calculate the friction force. What will be the value of friction force in this case? Calculate and tell me what is the value of the friction force. Is it mu mg? The friction force acting on the block, is it mu mg? No. Mu mg is the limiting friction force, that is the maximum value of static friction that is possible. So first calculate that limiting friction force. Limiting friction force is denoted by Fs, not this F, that is mu mg, that is mu n, and n here is equal to mg. So mu will be 0.6, m will be 5, this is 10. So this one will be 6 into 5, that is 30 Newton. So is the applied force is more than limiting friction? No. Means unless applied force is more than limiting friction, the friction force at that moment is equal to the applied force due to self-adjusting property of the friction. Okay, so at this moment what will be the friction force? It is only 25 Newton. So what will be the net force on this block? 0. Net force on this block 0 means with respect to the truck surface, the block has no acceleration. So when you try to pull some object, if you are applying some force, will it move? No. If you increase the force by small amount, you will find that friction force will also increase by small amount, and that will be always equal to your applied force until the limiting value is reached. Once your applied force exceeds this limiting value, then you are able to move that object. Means friction cannot increase further. So friction is self-adjusting, but not indefinitely self-adjusting. It has a upper barrier up to that limiting value. Suppose it is increasing. If it is increasing indefinitely with the applied force, then nobody can never move an object. Okay, so friction will increase initially, then once limiting value is reached, its value is fixed. It cannot increase further. Then your applied force will increase further and producing acceleration, it will move. And even in that case, the friction force decreases from this limiting value, because now the kinetic friction starts acting, not the static friction. So in this case, applied force is 25, but the limiting friction is 30. So applied force is less than limiting friction, so limiting value is not yet reached. So friction increases its value up to the applied force. That means if that is 25, it is also 25. But if the applied force is beyond 25, then friction force cannot go beyond 25. If applied force suppose increases and it will become this greater than 30. Here we find the static friction force, that is limiting friction is 30 Newton. If you suppose apply the force 32 Newton, then can friction increase to 32 Newton? No. In that case, the body will accelerate with respect to this surface, or the body will move with respect to this surface and it will accelerate. Now, and if the applied force is less than this limiting value 30, the friction will increase its value to cancel your applied force, and as a result net force on the body is 0. So the body will not move with respect to this surface of the truck. So to move the body, you have to produce an acceleration which will create a pseudo force on this body which is greater than limiting value of the friction, means greater than 30 Newton force has to be applied by the pseudo force. Then only the body will move with respect to the truck surface. Okay. So don't forget this one, that whenever applied force is less than friction, limiting friction, then value of the applied force and friction force will be equal. So most of the time many students write that, okay fine, this is 25, this is 30, so resultant force along this direction is 5, so friction will pull the object. That is not true. Friction cannot pull the object, friction cannot help in moving. Okay, so don't write that due to the direction of friction more force is there, body will move in the direction of friction. That is not true. Okay.